Hey guys, this is Arvind. You are watching Learn with Arvind. In this video, we'll be discussing on constraints, types of constraint, and in the later part of the video, we'll be discussing on degrees of freedom. Let's start with the example of a constraint. Consider we are having a key, and that key is tied to a string of length 1 meter. Now, if you grab one end of the string and if you spin that key would move in a circular motion. This key is restricted to move in this circle, in the circular motion. There is restriction on this key. This is what we mean by constraint. Here the constraint is this string. The string is what constraint is. If a motion of a particle or system of particle is restricted to one or more conditions, this restriction is what we mean by constraints. Now you may ask a question, why do we even need constraint? Why do we need this concept? The reason for this constraint is it simplifies the mathematical description of a system. We will see that you will know that while we are discussing about degrees of freedom. That's in the later part of the video. Types of constraints. Constraints are mainly classified into two types. That is holonomic and non-holonomic constraint. The example for holonomic constraint is what we see in the previous case. In holonomic constraint, this constraint can be expressed as an equation. The condition of this constraint can be expressed in the form of equation. This is what we mean by holonomic constraint. If the conditions of a constraint can be expressed in the form of equation, this equation connects the coordinates of this system. This equation would be of the form f of r1, r2, and so on, t is equal to 0. Mostly holonomic constraint contains t, which is nothing but time. We already discussed the example for holonomic constraint, which is a particle moving along the circumference of a circle. Now take this for instance. Here the constraint is this string, which is nothing but the radius of the circle. This is a constant. So just a single generalized coordinate theta is enough to describe this system. So the constraint here is r is equal to a, which is nothing but the radius. A is the radius of that system. So the equation of constraint is mod r is equal to mod a. Now we will be discussing about non-holonomic constraint. If the conditions of constraints cannot be expressed in the form of equations, this is what we mean by non-holonomic constraint. Now let's just get into a basic idea of what an equation is. If you have an algebraic expression and if you could equate that to 0, if a polynomial contains equal to, then this is said to be an equation. Now let's see an example for non-holonomic constraint. Motion of the particle along the surface of the sphere, which is a special case of earth. Think we could generally go through the earth, that's we could tunnel inside the earth, but think of yourself, you could not go inside the earth. If P is a point at which you are standing, you could jump above the earth, you could stand on the surface of the earth. That is, you can be equal to the radius of the sphere and you could go greater than beyond the radius of the sphere. But you could not go lesser than this. This is what this equation means. So here there is no equal to, it's greater than or equal to. So this is how non-holonomic constraint would look like. Now constraints are further classified as Rheonomous and scleronomous. In Rheonomous constraint, it contains time as explicit variable. In Rheonomous, the equation of constraint contains time, whereas in scleronomous, the equation of constraint do not contain time. Let's make this as a sentence and give it a definition. In Rheonomous, the equation of constraint, sorry, this is not equation of motion, the equation of constraint contains time as explicit variable. And Rheonomous, the main thing you should remember is it contains time. In scleronomous, the equation of motion do not contain time as explicit variable. Now we will be seeing the example for Rheonomous and scleronomous. The example for scleronomous is simple pendulum. It's a mistake, sorry about that. The example for scleronomous is simple pendulum and Rheonomous is rolling disc on a 3D plane. Reason is in simple pendulum we will be having only position coordinate, but in the case of rolling disc we will be having position and velocity coordinates in the equation of constraints. This is what we mean by Rheonomous. This is a Rheonomous constraint since it contains time. Velocity is a time derivative of position coordinate. Now we will be discussing about force of constraint. Consider this example we saw before. Here the force which keeps this particle, which restricts this particle, this is what we mean by force of constraint. Here it is the tension force along the string. So the tension is the force of constraint in this case. Now we will be defining this force of constraint. Forces which restrict the motion of a particle or system of particle. This is what we mean by force of constraint. This force of constraint would be perpendicular to the surface of the constraint if the motion acts parallel to the surface of constraint. If it's parallel, that's when motion acts parallel, then the force of constraint would act perpendicular to the surface. Now the advantages of using constraint, we've already seen that. Why do we even need constraint? That's what here also. Now the difficulties introduced by constraints. The coordinate array, that's the position coordinate, it is no more independent. It's really a difficulty introduced by the constraint. The second difficulty is the forces of constraints are not known initially. These forces, we don't know that while we are starting about the problem, while solving the problems. But these difficulties can be resolved. This can be solved. The first thing is, the first difficulty could be solved by introducing the generalized coordinate instead of using Cartesian coordinate systems. The second difficulty is solved by making the constraint, that is the making the forces of constraint disappear. We will be considering the cases where the forces of constraint is 0. That's what the second one means. Now we will be discussing on degrees of freedom. Degrees of freedom. It is the minimum number of coordinates required to specify the position of dynamical system. For instance, take a Cartesian coordinate system which consists of two particles P and Q. P of x1, y1, z1 and another particle Q of x2, y2, z2. Now the degree of freedom in this case is 6 coordinates. More than saying degrees of freedom, the total number of coordinates required in this system is 6 coordinates. But what we are talking about is the minimum number of coordinates. It is not necessary for us to take into account all the coordinates present in a system. So the degrees of freedom, that is what is essentially we require. it is sufficient to describe a system. So the formula for degrees of freedom is 3n minus k, where k is the number of constraint and n is the number of particle. For instance, take a single object which will have only one constraint. So the degree of freedom in this case will be 2. We will be seeing the generalized coordinates and further concepts in the upcoming videos. Do share, subscribe and like our videos. See you in the next video, guys.